And we're live. Let's go.
Of this kind, where it's B given formula for the conditions of all the scenarios. So in the end, we have a formula for the conditional probability A is given B based on the data of the problem, which were probabilities of the different scenarios and conditional probabilities of B given the A. So what this calculation does is basically it reverses the order conditioning. Are given conditional probabilities of this kind, where it's B given A, and we produce new conditional probabilities where things go the other way. So schematically, what's happening here is that we have a model of cause and effect. And so a scenario occurs, and that may cause B to happen or may not cause it to happen. So this is a cause-effect model. And it's modeled using probabilities such as probability of B given AI. And what we want to do is inference, where we're told that B occurs, and we want to infer whether AI also occurred or not. And the appropriate probabilities for that are the conditional probabilities that A occurred given that B occurred. So we're starting with a causal model of our situation. It models from a given cause how likely is a certain effect to be observed. And then we do inference, which answers the question, given that the effect was observed, how likely is it that the world was in this particular situation or state or scenario? So the name of the Bayes rule comes from Thomas Bayes, a British theologian back in the 1700s. It actually, this calculation addresses a basic problem, basic philosophical problem, how one can learn from experience or from experimental data in some systematic way. So the British at that time were preoccupied with this type of question. Is there a basic theory that we can, about how we can incorporate new knowledge to previous knowledge? And this calculation made an argument that yes, it is possible to do that in a systematic way. So the philosophical underpinnings of this have a very long history and a lot of discussion around them. But for our purposes, it's just an extremely useful tool, and it's the foundation of almost everything that gets done when you try to do inference based on partial observations. Very well. Till next time. The order of conditioning.
The only, okay. Let's see, is there a, oh, cool. Nice, there's a link. Let's see when the first assignment is due. Oh, no, the calendar. So the problem set 1 is due on the day of this lecture, maybe. It could be like at night, though, so maybe we could take a look. The assignment. It's probably good to do. Let's see. Express each of the following events. In terms of the events, A, B, and C. Okay, A, B, and C are events. An event could be a set of outcomes, could be a set of multiple outcomes, could just be, yeah, so, okay. So this is an event. There's an event called A like this. At least so you kind of look at this. At least one of these happens. So we could kind of give an example. Like what happens if these were just distinct events? So they each kind of have this. So at least one of the events A, B, C occurs. So that, like, if we did A union B union C, that would be equal to A, B, C. And so this is at least one of these events occurs. If we say this event happened, then one of these happened. And if one of these happened, then it has to be one of these. So if we have an event E, then we say, and event E occurred. That implies that an outcome in E happened. Yeah, I mean, that's the case for continuous and discrete. So if we say an event occurred, so then we say at least one event occurs. One of the outcomes in E happened. So let me say at least, so if we say, and if we just do A union B union C, then an outcome in A union B union C happened. That means A occurred or B occurred or C occurred. At least one of the events. Maybe multiple of them happened. If we have A is equal to AB and B is equal to B, C is equal to C, then we do A union B union C. And in fact, it was the case that B occurred, B happened, then both events A and B occurred. At most, one of I guess we just got to get rid of the intersection. So it's like A, B, C. I guess one way to kind of think about it is back to this kind of like moment generating function thing. It's this like box, and something happens, some outcome happens. So you could kind of look at it like it's this box where some outcomes happen, but you can map that outcome to an event. And so it could be that like outcome 1 happens, outcome 2 happens, outcome 3 happens, and so on. And it could be the case that A happens, B happens, A and B both happen. A and B and C happen. Could be the case that just C happens. Could be the case that none happens. And so there's this kind of like sequence of events that are happening where it's like A happens, then like A and B, then like B, then like A and B and C. Maybe we should kind of do like A and B happens, and then B happens, and then A and B and C happen, and none happens, and just C happens, then A happens again, then A happens again, then A and B happens again, and so on. Express each of the following events. This is an event. An event is a set of outcomes. Okay, that's a good way to think of it. This thing is a set of outcomes. What set of outcomes is that? Yeah, so we kind of start with A, B, and C, and we should get rid of all the outcomes which belong to the intersection that belong to multiple of these events. So it's kind of like A, B, C. So I want to like get rid of all these events. At most. Subtract away A and B and C union with A, or A and B union with A and C union with B and C. Set of outcomes. At most. None of the events. Kind of want to look at, this stuff out here. A or B or C, sigma minus this. I guess it would just be the complement of this thing. All three events occur, A and B and C. Exactly one of them. So this is the difference between this and this. Exactly one of them occurs. So I think we want the okay, exactly one. So it would be this and this and this right here. These are all the outcomes so that just one of these events occur. So the at most one would be basically the same thing. And it would also be like this stuff out here. Events A and B, but not C. This is an event. It's a set of outcomes. A and B, but not C. It's just this. Set of outcomes. One way to kind of draw this a little bit is like, say we got like A1 over here, we got A2, A3, A4, we got B1, we got B2, we got B3, we got B4, and here we got C1, we got C2, we got C3, we got C4. These are kind of, more discrete kind of outcomes. So the outcome, A and B occur, but not C. So here would just be A2 and B2. Those are the outcomes. Those are the outcomes such that A and B both happen, but not C. Either event A occurs, or if not, B also does not occur. It's almost like two separate things. So we have like A, it's almost kind of like we have like two outcomes. So this is A. Either event A occurs, or if not, then then B does not occur. So A is not occurring. So we're kind of like out here. B does not occur. So it's kind of the overlap between these. I think it's kind of like all the outside kind of here. I wonder if this is fun doing the homework assignment. 3 heads, head. Yeah, I don't know if I want to do the assignment.
Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, so let us start. So as always, we're going to have a quick review of what we discussed last time. And then today we're going to introduce just one new concept, the notion of independence of two events. And we will play with that concept. So what did we talk about last time? The idea is that we have an experiment and the experiment has a sample space, omega. And then somebody comes and tells us that, the outcome of the experiment happens to lie inside this particular event B. Given this information, comes and tells us that, the outcome of the experiment happens to lie inside this particular event B. Given this information, it kind of changes what we know about the situation. It tells us that the outcome is going to be somewhere inside here. So this is essentially our new sample space. And now we need to reassign probabilities to the various possible outcomes because, for example, these outcomes, even if they had positive probability beforehand, now that we're told that B occurred, those outcomes out there are going to have 0 probability. So we need to revise our probabilities. The new probabilities are called conditional probabilities, and they're defined this way. The conditional probability that A occurs.
I was thinking about this, like as I was going to sleep last night. You could say the probability of B given A. You could also say this is just like a whole new kind of probability distribution where you just say it's like the probability, under the universe that A happened of B. It's kind of like this. These are kind of like equivalent. Maybe even like a third way would be you'd say the probability of B maybe it's like probability of B under sigma A, basically. I guess like sigma is equal to A. Yeah, maybe this is kind of like way to write it. Where PA of B is the probability of B under sigma is equal to A. Just call it sigma A, I guess. Where like, but the probability of A is the probability of A under just sigma. It's kind of like another way to write it. And we have these kind of like random variables and stuff. And you say like the probability of B given A. This could be a random variable. This could not. You say it's a random variable before. We're just talking about outcomes and event is an event and outcomes in the event. So anyway, yeah.
That we're told that B occurred is calculated by this formula, which tells us the following. Out of the total probability that was initially assigned to the event B, what fraction of that probability is assigned to outcomes that also make A to happen? So out of the total probability assigned to B, we see what fraction of that total probability is assigned to those elements here that will also make A happen. Conditional probabilities are left undefined. Elements see what fraction. So out of the total probability assigned to B, we see what fraction of that total probability is assigned to those elements here that will also make A happen.
Yeah.
Conditional probabilities are left undefined if the denominator here is 0. Easy consequence of the definition is if we bring that term to the other side, that we can find the probability of two things happening by taking the probability that the first thing happens, and then given that the first thing happened, the conditional probability that the second one.
Conditional probabilities are almost like logarithms in the sense where you say like, okay, we say, all right, log base 2 of 5, like what is this? Well, like this is defined as the number, like 2 to the what is equal to 5. We just say like, this number is this thing right here. Kind of similarly, when we're talking about conditional probability, talking about A and B, and we say probability of A given B. So it's kind of like B happened. It's just the proportion of A that's in B, essentially, like the kind of like ratio of this to this. It's kind of interesting. It's like probability of A given B is a ratio, is a percentage. I feel like not too many things I kind of come across are like really defined as like ratios and percentage. It's like the ratio of A inside of B. That's also inside of B. Interesting.
Then we saw last time that we can divide and conquer in calculating probabilities of a mildly complicated event by breaking it down into different scenarios. So event B can happen in two ways. It can happen either together with A, which is this probability, or it can happen together with A complement, which is
the ratio of A to B, the fraction of A to B.
Probability.
A to B.
So basically,
A over B.
Saying that the total probability
fraction of A
B is the probability of this, which is A intersection B, plus the probability of that, which is A complement intersection B. So these two facts here, multiplication rule and the total probability theorem, are basic tools that these two.
You say the probability of B is equal to, okay, A intersect B and then A complement intersect B.
Facts here, multiplication rule and the total probability theorem are.
Total probability theorem. It's kind of useful when you have information about probability of B is equal to probability of A plus probability of A complement.
Basic tools that one uses to break down probability calculations into simpler parts. So we find probabilities of two things happening by looking at each one at a time. And this is what we do to break up a situation into different possible scenarios. Then we also have the Bayes rule, which does the following. Given a model that has conditional probabilities of this kind, the Bayes rule allows us to calculate conditional probabilities in which the events appear in different order. You can think of these probabilities as describing a causal model of a certain situation, whereas these are the probabilities that you get after you do some inference based on the information that you have available. Now, the Bayes rule, we derived it, and it's a trivial half-line calculation, but it underlies lots and lots of useful things in the real world. We had the radar example last time. You can think of more complicated situations in which there's a bunch or lots of different hypotheses about the environment. Given any particular...
All right, guys, I think I'm going to hop off. Kind of spacing out. All right, that's good. See you later. Peace.